Chapter 8, slides 1 through 14. We're going to continue this chapter talking about alkyl halides. Right, so these types of carbon species with the functional group of bromine, chlorine, iodine are going to be the focus again for this chapter. And we're going to look at two more mechanisms, namely the elimination reactions that can be undergone by these alkyl halides. So I'm not going to cover again all of the physical properties of an alkyl halide because we already discussed them, right? The boiling points, melting points, and solubility trends for these types of functional alkanes. So let's just move to these two mechanisms. We're going to shift gears a little bit. Remember that when we were doing SN1 and SN2, the N, right? So for SN1 or SN2, the N was the nucleophile, right? That's what the N stood for. We were using a nucleophile to substitute with the leaving group. In this chapter, we're going to be using species that look just like the nucleophiles, but instead of calling them nucleophiles, we're going to call them bases. Why? Because they're not going to attack the carbon of the alkyl system. Now remember, we spent an entire chapter substituting at that carbon. We had a dipole caused by the very electronegative leaving group. That's what makes the alkyl halide reactive. And our nucleophile was focused on attacking that carbon. That's the carbon where the new bond was going to form, right? So we were exchanging or substituting out at that carbon. That is not the position of reactivity anymore. I mean, it's still reactive, but that's not where our negative species is going to be attacking. Instead, we're going to be looking at the carbon next door to the leaving group. So let's take a look down below. A nucleophile in a substitution reaction, the nucleophile would be a negative species. I don't know, let's say it was OH minus. Okay, let's do an SN2 as an example. Okay, the OH minus would use its lone pair and substitute at the carbon bearing the leaving group. And you would get this new molecule, where the nucleophile was an OH in this case. All right, now I'm still going to use an OH, and I'm just talking in general terms right now. Okay, I'm just showing you general. There are two elimination mechanisms. One's called E1 and one's called E2, very similar to SN1 and SN2. And you will see similarities between them. But what you'll notice is that the OH does not become part of the new product. A new pi bond is formed. So the product of an elimination, whether it's E1 or E2, is going to be a new pi bond that wasn't there before. I can still use the same type of negatively charged, compound, but it's going to behave differently. Instead of going after the carbon bearing the leaving group, it's going to go after the carbon next door. Okay? How? Well, hopefully the carbon you're looking at next door has hydrogens, and we're going to use it like a base. So our nucleophile is not going to attack the partially positive carbon. Our base, again, it could look like the same species, you've got to determine this, is going to go after a hydrogen next door. That hydrogen, right? So acid-base chemistry. Specifically at the carbon next door to the leaving group. So you're going to remove a hydrogen on the carbon next door. And again, you have to include two carbons. If you don't, you're not going to get a new pi bond. What would the double bond be between carbon and the same carbon of itself? That doesn't make any sense. You have to involve two carbons. One carbon, the blue one here, has the leaving group. The other carbon next door has the hydrogen to give. Okay, so that's the new area of reactivity. So the base, if you will, is going to grab the proton, and then the proton will leave its electrons behind, but it's not going to dump it into the atom. It's going to form a cascade. And you can see through this arrow pushing, plucking off the hydrogen cascades the electrons in and pushes the leaving group out. So this is the general elimination scheme that we're going to be considering. So we're going to learn first E1. Why? Well, I like to do E1 first because we just finished SN1 in substitution chemistry. And you're going to see a very, very, very close pattern here. And I'd like you to change this nucleophile now to base. Okay? Because we're not talking about nucleophiles, we're talking about bases. But we're really kind of talking about the same thing, right? Bases, nucleophiles, they're pretty much the same species. We just define them depending upon what they do. An OH minus could be a base, and OH minus could be a nucleophile, as we saw in SN1 and SN2 chemistry. Specifically SN2 with the O minus. Okay, so E1. Key points to an E1. Stepwise mechanism. Okay, that means that there's probably some intermediates. Well, that's similar to SN1. There's a carbocation intermediate. Oh yeah, yep, we saw that in SN1. And because of the carbocation intermediate, there are possible rearrangements if need be. Yep, check, check, and check, right? That sounds just like an SN1. And we'll talk about that. So let's begin. Notice that I'm starting with an alkyl bromide. So the bromide is my leaving group. Notice that I also started with a tertiary alkyl bromide. And I did that because I know there's going to be a carbocation intermediate, and I'm just going to put my best foot forward and start the ball rolling with, the right thing. If I'm going to form a carbocation, let's do it at a tertiary position because that's going to be the most stable. So the first step is solvolysis. In other words, leaving group leaves. So far, this is looking just like an SN1. Here's our intermediate. Second step. Stop. Look around. Are there any possible rearrangements to consider? Not really. This is tertiary, and that's the best I can do right now. But I always want to make sure I stop and consider all the possibilities. It's a good habit to get into. Okay, we're good. Let's move forward. Next step, introduction of our base. Let's, just for, I don't know, we can consider anything really. Let's use ethanol. Okay, and maybe a little bit of heat. And here's where things get interesting. I have the carbon bearing the carbocation. And I saw that in an SN1, a weak nucleophile / solvent is going to attack that and form an ether. But that's an SN1. I'm doing E1. So I have to involve one of the carbons next door, and there's 3 carbons next door. It just happens that all 3 of these are the same, so it doesn't really matter which one I use, right? Because they're all CH3s. So in this case, it's kind of easy because I don't have to worry about which one. I'm just going to pick one. And I'm going to use the solvent as the base. Okay, so this is my base. Instead of my nucleophile. It's also my solvent. And I'm going to just, instead of using that species as the nucleophile, I'm simply going to use it as the base. Grab the hydrogen and cascade those electrons towards that very needy, empty orbital of the carbon. You have a carbocation, it doesn't have an octet. So this is what heightens the acidity of the carbons, hydrogens next door. Normally, you guys might say, well, in ARIO, a carbon that has a hydrogen, just a regular CH3, is not very acidic. And it's not. However, the situation now that we have is that there's an octet lacking in the carbon next door. And that actually ramps up the acidity of those hydrogens. Why? Because if you imagine dumping the electrons into the carbon that we just plucked the hydrogen from, it has a positive charge right next door. It would basically do exactly what I'm showing with this arrow, is that it would fold up into being a pi bond so that everybody could be happy, because the net result of that is a new pi bond and everybody's octet is met. So up until this point, right, after this, you do solvolysis and you stop, you look around for rearrangements. This is the only differing factor between SN1 and E1, is how the species behaves. Between SN1 and E1, right there is, notice that that's the only difference, is how it behaves. It's not even a different molecule than we've seen in SN1. So we'll get to that, but let's finish out talking about E1 first. The rate for this E1 reaction, again, the 1 stands for first order. Why? Well, it's probably not surprising that the rate can be written as the K, which is the rate constant times the concentration of the electrophile. The electrophile being your carbon-based system with the leaving group on it. All right, that's your electrophile. Okay, so if that's my electrophile, then I know that I'm making a carbocation out of it, so there's going to be an intermediate. So when I try to sketch the energy diagram here, here is the starting material, electrophile. I'm going to form some intermediate carbocation, and then I'm going to form the product in this case. Okay, I know that because it's first order, that means that enough experiments were done to tell me that in trying to increase the concentration of the nucleophile doesn't really, or the base, I should say in this case, doesn't really do anything. It only seems to be dependent upon this first step, which ends up being the rate determining step. So I'm telling you the first step is rate determining for these reactions, and we're seeing an intermediate. How might we model the E1 mechanism using our hands? Okay, so let's go back and start talking about all of the things that we have to consider in an E1. You should feel very comfortable with all of the things we're going to talk about, because you'll see some very familiar slides, just like this one, right? As I mentioned, after solvolysis and the formation of a carbocation, right now it's just like an SN1, right? Leaving group leaves, step 1. Step 2, stop. Look around. Can I do better than this secondary carbocation? I sure can. There's a hydrogen next door. And that would be a great empty seat right there, because that would be a tertiary carbocation, or a tertiary empty seat. So if I hydride shifted, I could get my carbocation to be at the tertiary position. And that thermodynamically, stability-wise, is better. So this mechanism, when you have a rearrangement, you'll end up having 2 intermediates in your energy diagram. And the second one you draw should be a little bit lower in energy, because it's more stable than the first one you drew. Once you've spent your coupon on a hydride shift, you can't keep hydride shifting down the row. Like if you saw a tertiary group, like a tertiary position four carbons down. You can't like hop, 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 hop. It would take too much time and energy to do so. So this is a fast shift rearrangement, and it typically only happens once to someplace that is much more stable, and then you're done, and then it continues on. So we're done. We've spent our coupon. We made our shift. We're better off than where we were. And then you would continue on your journey for E1. E1 base chemistry. Okay, I'm not going to show you the products here because we have a few more things to discuss. Alkyl shifts are also possible, and I also wanted to note that similar to SN1, you can use acid and protonate an alcohol to make it a good leaving group. So it kind of adds to our repertoire of possible leaving groups. We can protonate an OH and make it water. And then we can do our solvolysis. Water leaves. You form a carbocation. This is a shame because you started with a very chiral species. Same thing with the other one up above. Why anyone would want to start with a really expensive chiral molecule, right, with a stereocenter, and then you're just wrecking it, right? After that group leaves, you have destroyed the stereocenter. You've flattened it out to an sp2, and we know that if it did SN1, you'd get attack from both sides, and if you do E1, you're going to form a new double bond at that position, and sp2 carbons can't be stereocenters. So it is kind of bizarre starting with an expensive chiral molecule, but whatever, we'll keep going. I have a secondary carbocation at this position. I noticed that next door, I would love to have my carbocation there because it could be tertiary, but there's no hydrogens there. There are methyl groups. So a methyl is an alkyl group. There's lots of different types of alkyl groups. So we've got this methyl, just like the hydrogen, unplugs its 2 electrons and hops over. This gives us a tertiary carbocation. And then it can go on and do E1 chemistry, right? I'm not going to show you the products of these yet. We can come back to these. Okay. So these next few slides are going to look very familiar because they're pretty much the same slides we saw for SN1. Now, if you've realized, the mechanism for SN1 and E1 are so similar, and it's a little scary how similar. So their needs are going to look the same as well. Alkyl halides, because we're forming a carbocation as an intermediate, then we're going to prefer tertiary over secondary over primary over methyl. It's the same slide as SN1. The needs are the same. The first step is the rate determining step. So it's the hardest thing to do is to form that carbocation high energy intermediate. So the trend observed is due to induction, right? We want to stabilize the carbocation intermediate. That's the whole purpose for this trend. And it makes sense, right? The more electron donating groups you have on the carbon that becomes empty, the more stable it's going to be. Just like SN1. Here's that carbocation stability trend that I showed you in the SN1. Tertiary is going to beat out primary with lots of resonance, which is about the same as primary with resonance, with regular resonance, which is about the same as secondary. So secondary and any type of resonance, I would say the only thing that beats out these primary resonance is if you had tertiary with resonance. That would be like the best thing ever. Secondary is better than primary, and primary is better than a methyl. And you know what's at the end of the chain here? The worst of the worst is vinyl. The orbitals are just not lined up you can't resonate a carbocation on a vinyl system because the empty p orbital is not in line with the p orbitals of the pi bond. So there's no resonance, and the emptiness, the empty p orbital, is one of the hybrid orbitals, and it's 120 degrees away, really far away. It can't even get that mild inductive overlap, even if there is a donating group next door. So vinyl is the worst. There's just nothing able to stabilize it. How do you relate this energy diagram to the SN1 mechanism? Well, as I mentioned, it's the exact same trend. Because the first step of both of the mechanisms is exactly the same, they have the same trends, and it's the first step. It's the rate determining step. So things are all, pointed at E1 and SN1 being very difficult to decipher between. Leaving group effects. Guess what? A leaving group is a good leaving group is a good leaving group, right? What makes a good leaving group a good leaving group? Well, when it gets ejected, right? So when the leaving group leaves, the leaving group typically, not always, when water leaves, it leaves as water, right? So when you do H2O plus as a leaving group, it leaves as a neutral compound. That's great, right? Because it's stable. When you have a leaving group that leaves and it has a negative charge on it, we know how to decide how stable it is. We use ARIO. ARIO helps us to decide how good a negative charge stability is. In this case, we're using ARIO to look at how stable the negative charge is when the leaving group leaves. And if it's stable, that means it's more willing to go. And that's why iodine, bromine, and chlorine are great leaving groups, because they're very electronegative. And when they leave as I minus, Br minus, Cl minus. And you guys already knew these were good leaving groups, because when you were doing acid-base chemistry, if you had OH minus and we gave you HCl, OH minus grabs the hydrogen. Oh gosh, look, it kicks off a Cl. Cl is a leaving group. These groups as leaving groups are not new to you, except in the past we had them attached to hydrogens. Now we have them attached to carbons. And then it offers up a couple mechanisms to consider, right? SN1 or SN2. Now we have E1 to consider in more complex carbon-based systems. But the leaving group is the leaving group. It's the conjugate that gets ejected. And if it's very stable, then it makes a great leaving group. It's not going to come back and start trying to do more chemistry. So it has to be stable once it is left. It also should want to be polarizable so as to stabilize the transition state on its way out. Polarizable, remember, is that squishiness, right? That able to morph the electron cloud as it leaves. So we can again write our elimination. Starting material, high energy state, intermediate, carbocation, and to our product. This is, you would say, this is an energy diagram that does not show a rearrangement. It only has one intermediate. The reactivity of the base, well, the base comes in here. This is when the base takes off a proton. That transition state is the base removing a proton. That is not the rate determining step. So if I have rate equals K times the electrophile, meaning the alkyl halide, if I increase the concentration of the base by 2, what happens to the rate? Nothing. Rate stays the same. Just like SN1, right? It's only reliant, it's first order, it's only reliant on this rate determining step. If you increase the concentration of the electrophile by 2, the rate doubles, right? So you can see this really nice relationship. What about solvent? No surprise, as you saw from the things I was using as the base, that the solvent tends to be the base that we're using. The solvent and the base will be the same entity, just like we saw in SN1. And that we want them to be protic solvents. Why? For the same reasons that we saw protic solvents stabilizing the or helping to solvate and stabilize the removal of the leaving group, solvolysis, right? We still want that strong force, strong polar force surrounding the leaving group. We also want to stabilize the carbocation, right? So this could be the same exact slide, right? It assists with leaving group stabilization. That's what's shown in the picture here, right? The very electropositive hydrogens congregate around the electronegative bromine and help carry it away like the paparazzi. And also the protic system also assists with stabilizing the carbocation, right? The empty octetless carbon. So we want those protic systems because they're highly polar and help to stabilize all of these highly energized systems, the intermediate and the leaving group. Okay, so I wrote a reaction here. I've got an E1 going. And the electrons, right, the water's going to solvolysis, solvate the leaving group. We're going to form a carbocation. It's secondary. I need to stop, look around. Can I do better? No, I'm good. I'm going to stay put. So now I'm going to do a new one. So I'm going to have the water be a base, not a nucleophile. But what you're going to notice is that here's the carbon of the carbocation. Here are carbons next door. Each of those yellow carbons next door has hydrogens. If I remove one of the hydrogens on the left using the water as the base, I get that double bond. Okay, but what if I use the hydrogen on the right? Okay, what does that do? That is going to give me this. Wait a minute. What if, now bear with me, what if, because it's a single bond, what if the carbocation, because it's spinning around and round, those bonds are single bonds, they're spinning, spinning, spinning. What if at the moment that it was spinning and both methyls were in the same direction, I removed a hydrogen? So the oxygen grabs the hydrogen, acts like a base, kicks the electrons in. Now I have formed that. So the three possible products for this reaction are all drawn for you in blue. Oh my God, there were three possible products for this E1 reaction. So why is it that the major product is the one circled in red? This is going to kind of go back to our Newman projections to think about the stability of the intermediate and precisely around those rotations. But there's also one other thing that you probably don't have in your repertoire yet, in the back of your mind to understand yet. And that's the stability trend for an alkene. So the trans isomer is going to be more stable by about 1 kilocalorie per mole than the cis isomer. So I've got those drawn here. And 1 kilocalorie per mole is actually pretty decent. This is due to what? Why is the trans, right? So this is the trans. The two methyls are opposed to one another versus the cis, same side. Why is the trans more stable than the cis? What top 3 answer in organic chemistry could you use to explain this? Well, if you said steric hindrance, you are correct. When you have alkyl clouds that are closer together, they're going to bump into each other. So here's 2 alkenes down below. Which one is more stable? A or B? Both of them have steric hindrance going on, but which one has more steric hindrance? Well, I'd argue that the bigger the group, the harder it is to get out of its own way. So there's way more steric hindrance here than there is there. And I'm trying to show that using the steric hindrance. So there you have it. A is probably less stable due to more steric hindrance. Okay? All right, so how does that factor into my question here, right? Well, maybe I could say that the cis system has some steric hindrance there, and that's why the trans is preferred. Okay, but so I've kind of rationalized between 2 of them, but why is the other alkene not the major product? So we have to consider some more energies. When studied, and I will show you this. Now, how did people figure out in the lab the differences between these energies? Well, what you can actually run a reaction called hydrogenation, and we're going to learn about hydrogenation in chapter 9. Hydrogenation is doing chemistry where you basically saturate the carbon double bond with hydrogens. Notice that if you turned this butene into butane, they both would form butane. So they would both form the same product. So the product energy is the same energy because they're both forming the same product. If you saturate a butene, no matter if it was cis or trans, you're going to get butane. So what you can do is measure the energy given off, the delta H, when you hydrogenate these species. And the more energy given off, that means it must have started from a higher energy. If it goes to the same place, but it gives off more energy, that means that it started at a higher energy, right? Its potential is higher. So that's why when you hydrogenate a cis butene and it forms butane, right? 1, 2, 3, 4, total saturated with hydrogens, and you calculate in a calorimeter the delta H, it gave off 28.6 kilocalories per mole, but the trans only gave off 27.6. Therefore, their energies are related as shown. That's how we can figure out relative energies. Well, if you did this for a whole series of alkenes, what you would find is a trend called Zaitsev's rule. And the trend is thus that the more substituted a double bond is, the more stable it is. So you can think that those pi systems are stabilized by more donation. Just like a carbocation, the more donating you have the groups, the better off you are. So a tetrasubstituted, right, having 1, 2, 3, 4 carbon type alkyl groups around a double bond is better than a tri-substituted, which has only 3 R groups around. Doesn't matter the order either, just does not matter. What you'll notice is that all of the ones in the middle are di-substituted. Trans is lower in energy than cis, right? And we just showed that. The reason they're both di-substituted, but what changes them is the steric hindrance. And geminal, because there is some steric hindrance here, is actually lower in energy than the cis, and that's due to angle. Monosubstituted is the next up. So this is just having 1 carbon off of the system. And then ethylene is the highest. Ethylene just with no substitution whatsoever. is the highest in energy and thus the least stable of them all. So now you have a trend to follow that is really going to help you when you're predicting the products of new pi bonds, right? Especially if it's governed by thermodynamics. So we've got a few cues that we're going to be considering. This is very similar to the question we just asked, right? The bromine leaves, you form a carbocation. It's secondary. I'm not going to move it because there's no reason to. It's not going to go primary and it's not going to go secondary. There's no reason to move next door if it's going to stay the same, right? You're not going to do a lateral move. So secondary to secondary is not going to happen. No thermodynamic thrust to do so. Now we're going to show an E1 and we have our carbocation and we have our carbons next door here and here. And so we have some possibilities. Okay, if I deprotonate, call it A and B. No, I've got those, never mind. I should call them 1 and 2. So 1 and 2. If I deprotonate at 1, I have 2 possibilities, right? So this is if I removed a hydrogen at 1. If I removed a hydrogen at 2, I would form product C. This is my product distribution. These are all the possible major and minor products that I'm going to form. The relationship between A and C is what? These are constitutional isomers. The relationship between B and C, constitutional isomers. The relationship between A and B, go back to chapter 5, diastereomers. I know they don't have a stereocenter, but they are different through space. So they have the same molecular formula. They have the same connectivity pattern, right? Because if you named them 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, they're both pentene with the carbon double bond between 2 and 3. So they have the same connectivity, unlike product C, which has the double bond between 1 and 2. So they're both the same compound connectivity, but they differ through space, right? And they're not mirror images, so they're not enantiomers, they're diastereomers. That's how we classify cis and trans double bonds. So what we're dealing with here, when we have a mechanism, and you have, during the course of that reaction, if you have a choice, like we have here, between plucking off the hydrogens at 1 or plucking off the hydrogens at 2, this is called a regioselectivity issue. Oops. This is a regioselectivity issue. This is like, oh my gosh, do I pluck off 1 or do I pluck off 2? Ultimately, am I going to make the A-B variety versus the C, right? Because they're constitutional isomers. Usually, regioselectivity issues will lead to mixtures of constitutional isomers. Stereoselectivity issues, now you guys have already been dealing with this. This is, am I going to make A or am I going to make B? Am I going to come from the front or am I going to come from the back when you were talking about SN1, SN2? Those are stereoselective. We're not worried about which carbon to deal with. We knew what carbon to deal with. Once you identify that, you still have a choice through space. And that is the difference between diastereomers and enantiomers, right? But when you're looking at two possible products and their product mixture gives you constitutional isomers, that's when you know you're dealing with a regioselective issue. Okay, so let's sum it up. And this is the bottom line here. SN1 and SN1 and E1 right here. They both want a weak nucleophile or a weak base. And as we saw, those species look exactly the same. Water, ethanol, methanol, right? We noticed that for the substrate, the electrophile, tertiary is better than secondary is better than primary. Oh my God, this is the same. Solvent, they want protic. Leaving group, well, a good leaving group's a good leaving group is a good leaving group. Iodine's better than bromine's better than chlorine. So far, there's no difference between them. Rearrangements, common, because you're forming a carbocation. And stereochemistry, well, in SN1, you're going to get a mixture of both inversion and retention, front and backside attack. And for E1, you're going to get a more substituted alkene that's formed for thermostability. So going back to this case, this is going to help us decide stereoselectivity and regioselectivity. Right? So going all the way back to our elimination reactions in blue, I know that the more stable double bond is going to be the one that's di-substituted, not mono-substituted. So we can answer this question again. Due to Zaitsev's rule, the more substitution you have, the better. I also can point out that when you're considering removal of the proton, of the carbocation, it's a carbocation. So you're using a Newman projection, you can actually see the steric of the two groups being placed farthest away. So when you remove that proton, you're going to end up with the trans double bond. So ultimately, the bottom line, this is what I want you to walk away with. SN1 and E1 are going to be written like this. Why? As you can see, there's no distinguishable feature, is there? How the heck are we going to decipher when the conditions favor an E1 or an SN1? This competition is just not feasible to distinguish. You're probably going to get a mixture of both. It's very difficult to control. So when you're faced with a reaction mechanism that where it's asking you to decide what type of reaction, you'll be able to decipher it away from SN2. You might say, oh, this is a strong nucleophile, it's going to do SN2. If it has a weak nucleophile / base, then and tertiary electrophile and protic system, you're going to be like, well, it could do an SN1 / E1. That's going to be your answer. Okay?